Welcome back. So now let us see through what is known as the Schmidt orthogonalization procedure how to arrive at the orthonormal basis functions by phi 1, phi 2, phi 1 of t, phi 2 of t and phi n of t from the set of signals S1 of t, S2 of t and so on. We have Sm of t. So let's call this as Si of t. So we have got with us these signals which we have selected to represent binary messages. Now through this procedure he has told us that from these signals itself you can arrive at the orthogonal functions. So the procedure starts like this. So step 1, first we have this with us this. So we will start with representing some phi 1 of t as S1 of t divided by root of E1. So these are all energy signals which are having finite energy. So we will start with phi 1 equal to S1 of t root E1 t. So that means what? S1 of t can be represented like this, root E1 phi 1 of t. So this tells us that phi 1 of t is a unit energy signal whose amplitude is root E1 and this is a energy signal whose amplitude is 1. So energy is 1. So this is one waveform, a function of a set of orthonormal functions has been obtained like this. We define from S1. S1 is known to us. We can always find the energy of that signal and represent like this. Now next step would be we define. So step 2. So we define phi 1 to be like this, and let us define S21 to be S2 of t, phi 1 of t. We already know S2 of t. We have already obtained phi 1 of t. Using these two, we define the coefficient called S21 like this. Then let us define another function called G2 of t like this. S2 of t minus S21 phi 1 of t. Okay? So from this we can define phi 2 of t as G2 of t phi 2 of t as G2 of t divided by integral like this. Okay? So a normalized G2 divided by its energy. We have defined G2 to be S2 of t, S2 of t already known to us, S21 we have defined like this, and phi 1 t is known to us. So we will define phi 2 of t. Phi 1 of t is obtained, phi 2 of t we are defining like this. Now our objective is to generate phi 1 t, phi 2 t up to phi n t. Phi 2 t we have generated like this. Now we have to prove that this phi 2 of t is having a unit energy and phi 1 of t and phi 2 of t are orthogonal to each other. This, if you can prove, then two functions have been generated, and then we will go to next function like this. So let us see whether phi 2 of t is having unit energy. So this, if you do this particular integral energy calculation, phi 2 square dt. If you substitute this, you square this and integrate this, and the square you already have got this value, which will be something like this. So this will be squared, and got a constant like this, and this will be squared and integrated as this one. When you square this, this will become this, and this will become, sorry, this should be square root of it. And if you square this, you have got same thing here. This is a constant. You already integrate, you have got this constant. Now because of this integration results, and you do that, this will be equal to 1. That means phi 2 of t is having unit energy. Phi 1 of t is already we have defined it to be unit energy. This is having unit energy. Now similarly, if you do this operation, phi 1 of t into phi 2 of t dt, if you are able to do this, you will find this result is equal to 0. So here you will substitute phi 2 of t. Phi 2 of t, phi 1 of t, you already have this expression, and phi 2 of t, you substitute this in terms of this one, and you do the integration, which you do the substitution, you will find this will result in 0. Okay. So that way we can show that phi 1 of t is unit energy, phi 2 of t is unit energy, and phi 1 of t, phi 2 of t are orthogonal to each other. Similarly, if you go on, you proceed like this, then you can arrive at similarly, as a last step, if you do, what you will get is, we can show like this, g of t to be equal to si of t minus so without going into the all the steps, we can conclude that at the end of this procedure, g1 of t, phi 1 of t, phi 2 of t, and then go on proceeding like this, phi I of t can be obtained like this. Okay? Can be obtained like this. Now what are we doing? These steps will evolve from the previous steps, which already you have been given the text of this lecture, so you can always refer to that. So gi of t becomes this, and where si of t is this coefficient, and phi I of t can be gi of t. So what are we saying? Phi 1, phi 2, phi 1 we have defined. Phi 2 can be obtained from G2 like this, and phi 3 can be obtained from G3. G3 you will define from here and then substitute here and get the phi 3, and you can show phi 3 has got unit energy. Phi 3 phi 1 are orthogonal to each other, phi 3, phi 2 are orthogonal to each other, that we can also show. So, at the end, you will get phi I of t to be like this. G, suppose phi 3 of t is G3 of t. Now, G3 of t you will obtain from here, because S3 is known to us. You would have already got this j is varying from 1 to I minus 1. Suppose it is 3, I minus 1 is 2, maximum is 2. So, phi 2 will be known. When you are calculating G3, phi 2 only will be used. When you are calculating G4, maximum phi 3 only will be used. So, before previous function will be known to us, and therefore this can be generated and substituted here, and such functions can be generated. This is the Gram-Schmidt's orthogonalization process through which we are able to generate the set of orthonormal basis functions phi 1, phi 2, phi 2, phi n from the set of signals S1 of t, S2 of t and Sm of t, so that we can represent that as a linear combination of these functions. So, which will result in detecting, in designing optimum detection process. So that is all about the Gram-Schmidt's orthogonalization process. So as a very simplified version of this discussion has already been posted to you. You refer to that, and if you have any doubts, you can also always refer to Simon Heikin or any other book of your choice. So with this, we conclude our discussion on orthogonalization.